This is the strategy game Istanbul. The goal of the game is to collect a bunch of these rubies, and it's basically a worker placement game where there's 16 different spaces, each having different strategies toward getting these rubies. I want to talk specifically about the Teahouse.
Teahouse.
The way the Teahouse works is as follows. If I move to the Teahouse, first I say a number between 3 and 12. Let's say 7. I then roll the dice and compare the dice roll compared to the number I said. So I said a number 7, and I rolled an 8. 8 is, of course, greater than or equal to the number I announced. So I get the number I announced worth of lira, in this case, 7. If I had rolled a number that was lower than 7, I would not get 7 lira. I would only get a little consolation prize of 2 lira. One approach to the Teahouse could be to say low numbers. Like if you say the number 3, you're almost guaranteed to get 3 lira, the number that you ask for, because there's only a 1 in 36 chance that you won't get it. That means you have a 35 out of 36 chance you're going to roll a 3 or higher and receive your 3 lira. The drawback is 3 lira really isn't much better than the 2 lira consolation prize. You could take the opposite approach, saying high numbers. For example, I could say 12, and if I get it, that's great because 12 lira is way better than 2 lira. The problem is, I really don't have a very good chance of rolling a 12 or higher. I mean, I literally only have a 1 out of 36 chance of rolling a 12 or higher. So, if 3 isn't the best strategy and 12 isn't the best strategy, what is? What's the mathematically best number to choose when going to the Teahouse? Well, I looked into it. I'll show you my results. Okay, to show how I solved this problem, I started off with just labeling the numbers 2 through 12. All the possible combinations of dice that you can roll with 2 d6s. Now, I'm just going to shade this out because 2 was not one of the options, so I'll just gray that out for some reason. Let's look at the probabilities. Now, anyone who's played Settlers of Catan knows the probabilities of rolling any of these numbers with 2 d6s. The probability of rolling a 2 is 1 out of 36. A 3 is 2 out of 36. 4 is 3 out of 36. 5 is 4 out of 36. 6 is 5 out of 36. 7 is 6 out of 36. You might think this pattern continues, but this is where it actually tapers back down to 5 out of 36, 4 out of 36, 3 out of 36, 2 out of 36, and finally 1 out of 36 chance. If we added these all together, we would see we would get 36. That would be the total number of possible rolls. So let's look at the probability of equal or greater. Remember that the Teahouse says equal or greater. So again, we're not going to say 2, but we'll just go ahead and put this on here. The probability, of course, is 36 out of 36. I guess I'll just put that. Meaning you have a 100% chance of getting a 2 or greater. But again, we're not so concerned with 2, but I just want the numbers to add up. Let's start from this side just to make the counting easier. So a probability of getting equal to or greater than a 12 is 1 out of 36. But equal to or greater to 11, I have the 2 here plus the 1 here. So it's actually a 3 out of 36 chance. Same here. We have 3 out of 36 if we get a 10, but we have to add these other 2. That makes a total of 6 out of 36. 10 out of 36. I think you're getting the pattern here. 15 out of... And yes, the numbers came in perfectly. So these are the probabilities that you'll roll an equal or greater value if you say that number. Let's go ahead and put that into percentages. I'm going to just do that here. We can just give it an equal sign. Okay. Now, this mirrors what I had said earlier about how if you choose a 3, you're almost guaranteed to get it. And if you choose a 12, you're almost guaranteed to not get it. So the answer must be in the middle here somewhere. However, it's clear that
the further to the left you go, the lower the number you choose, the better your chances are. That's not exactly the pattern we want. In order to see what the mathematically best number to choose is, we also need to look at the payout. So payout would just be the value of what you say. So let's just go ahead and copy these down. It may seem a little redundant, that's fine. So this row, we're going to make this a little more interesting. Let's find the payout times the probability. And this might show us some interesting things. So for this, let's do a little formula. We'll do B3 times B4. Copy that formula, and we will paste just the formulas. Aha! Here we see something interesting. It's not a trend that's greater on the left or greater on the right. It has a midpoint that's higher than any of the other points around it, which happens to fall at a number 6. Let's go ahead and mark that as the local high point. Maybe there's something special about this 6 here. Is that the mathematically best number to choose? I'm actually going to argue that it's not. And the reason why is because you have a consolation prize of 2 lira. You're guaranteed to get 2 lira. So, getting 6 lira is great, but, this is from a baseline of 0, not from a baseline of 2. So let's make an adjusted payout times probability. So for this, we want to subtract 2 from the payout. So the payout row is B4 minus 2, and then let's times that by the probability. And now let's see where our higher point is. Higher, 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 lower. Aha! A new high point has emerged. It is this one. It is 7. 7 is the mathematically best number to choose when betting on the Teahouse. It has a high probability, but also a high payout. It's the place where the payout and the probability converge for the highest product.
My analysis of the Teahouse could end there. However, there's another game mechanic that really influences your strategy at the Teahouse, and that is this bonus you can get from the small mosque, where anytime you roll the dice, you're allowed to change one of the dice to a 4, or to re-roll both dice one time. As you might imagine, that can greatly influence your strategy at the Teahouse, so let's go back to the drawing board and look at it with this change.
To figure out how the dice bonus affects the Teahouse strategy was a little trickier. I started by making another table, labeling the numbers of possible dice rolls. But then this time I wanted to show all the different combinations you could roll in order to get that number. So for example, for a 2, there's only one combination. You have to roll 2 1s. To roll a 3, however, you could roll a 1 and a 2, or a 2 and a 1. A 4 is a 1 and a 3, a 3 and a 1, or a 2 and a 2. 5, of course, is a 2 and a 3. Or let's start with 1 and a 4, 4 and a 1, 2 and a 3, or a 3 and a 2. You get the idea. I'll finish filling out the table. Alright, and then to help myself visualize this and figure out how changing one of the dice to a 4 would affect the totals, I started by color coding these. Now I already know from previous working through this that these first 3 numbers aren't going to matter. If I change any of my dice to a 4, none of them are going to be 4 or less. So starting with this column, let's go ahead and just give it a nice color, and we'll give each successive column its own color. Alright, now let's look at every single possibility and try to figure out which ones we would want to change one of the dice to a 4. Well, basically that's easy. If either of the dice are lower than 4, then it behooves you to change that one to a 4. So of course, this one, no change. These two, no change. In fact, this column, no change. There's nothing less than a 4. The first time we get to something less than a 4 are these two boxes. Now, what number would this become if you changed the 3's to a 4? Well, of course, they become 10s. We have a color for 10s. Let's change that color code to the 10s there. Okay, would we change any of these? No, we would not. How about these ones? If we changed these 2's to a 4, either of these 2's, what would we have? Well, we'd have a 10. So let's change that to blue. In fact, this one, same thing. We'll still get blue. Okay, how about these 3's? What if we change these 3's? We'll end up with a 9. Let's find our 9 color. Add that to the 9's. These two would become 9. And lastly, if you change one of these ones to a 4, you'd get a 5. So now let's make a new column for totals here. We'll just add a little grid. My new totals mean I'm going to get 0 2's this way, 0 3's, 0 4's. How about 5's? I mean, I have an extra box here, but that's nothing in it. The only real 5 is if I change one of the 1's to a 4 and get a 5 that way. So there's 1 5. Alright, now this is already a much more interesting distribution than our previous numbers up here, right? We had a 1 out of 36, 2 out of 36, peaks at 7. Well, now we have a whole different distribution that kind of peaks at 10. Made a new little grid here, and let's put this line as probability of equal or greater, right? All of these are already out of 36, right? So 1 out of 36. This is 3 out of 36. I guess I'll just do this to all of them. Alright, and then on this column, this row, of probability of equal or greater, remember it's kind of helpful to start from the right because we're just going to add them up as they go. So probability of getting equal or greater to 12, even with the bonus where you can change one of the dice to a 4, you're still only 1 out of 36 chance. And same with the 11, it's not going to change either. We're going to end up with a 3 out of 36 by adding that together. Here's where it gets drastically different. Here we're going to have a 12 out of 36 chance of getting 10 or higher with the bonus of changing a dice to a 4. Here's 20 out of 36. 20. Alright, I forgot to do the thing where I put the equal sign, so let's go down the line, put the equal signs, and change these all to percentages. Alright, we now have a new distribution of the probability of getting equal or greater. But once again, the probability isn't the whole story. I mean, according to this, you could say 5 and you'd get it 100% of the time. But that's not necessarily the best payout, right? Especially the adjusted payout. If your consolation prize is 2, 5 isn't really that much higher than 2. Let's see if we can do better by factoring in the payout. Okay, remember for this, we're just going to say, in this case, I've got B11 minus 2 times the probability, so that's B19, and let's see what we get. All right, increasing, 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 increasing a little bit more before it finally decreases. So according to this, 8 is the mathematically best number you can pick, right? That's not to say you'll get it every single time. If you play on the Teahouse and you guess an 8, you could still roll too low. But over a large sample size, it's definitely the most payout, right? Like if you were to play on the Teahouse 100 times, you'd end up with the most money by choosing 8 every time. So that's it.
Alright, that's my tutorial on the Teahouse. I hope you found it interesting. Thanks for watching.